I got 15 components laid out here on the bench and they all need to be welded today. I've got 4 Franken wrenches to do, 3 on the front here and 1 on the fixture plate there, and bracket for an LED light. I've got 4 leveling feet to plug weld just here and 4 of these clamps to make up. They're designed just to screw into that fixture plate there. And I think if we add all of that up, that makes 15. Oh, there's this other bracket as well for a filter for my new plasma cutter. I need to filter the air, and this is the basis of the bracket that holds that filter just over there. So the thing about welding is it's a properly Jedi activity because you're holding a ray gun and firing subatomic particles at something, and you're controlling a pool of molten metal with your mind. It doesn't get much more Jedi than that. Oh, you bastards. It's easy to weld in industry because welding bays exist and they're purpose built for this kind of thing, and the dudes who work in them get really good at exactly the job at hand, you know? Welding at home is a bit different because every job is different, the environment is imperfect, and it presents unique challenges. So with this in mind on the to-do list, let's talk about getting that done and living to tell the tale. Okay, so future me here. All the welding has been done, as well as all the post-processing, the subsequent machining and grinding of some of the components and bluing them, whatever. And I'm not deeply ashamed of any of it. Well, I am actually deeply ashamed of that. We'll get to that, because I could have done a lot better there. Anyway, you've got to be critical of your own work if you want to be a decent welder. So all the projects turned out okay. The leveling feet for the milling machine turned out okay. They've been blued with this Birchwood Casey gun blue stuff, selenium whatever, and they turned out better than they need to be for something that's going to be hidden under a machine tool for the rest of its life. But it's going to be, as you can see, dead easy to tweak the height so I can get the bed of the mill dead level. And if I can do that, that means I can use gravity as a proxy for verticality when I need to set something up. So that's why it's kind of important to be able to align or level machine tools, right? Lathes, absolutely the same. This thing turned out okay too, although if you're not a welder, you'll be scratching your head and going, WTF is that? If you're a welder, you'll know exactly what this is. It's one of the most useful things you can have in the shop, and it's one of the best first projects you can build after you've learned how to just run beads on plates and do basic joints until, you know, that process has bored you senseless. The Franken wrench turned out okay. It doesn't look factory, but it looks like something that you could use to hold the body of an ER32 collet while you use the collet spanner, the nut spanner, to tweak, to loosen or tighten a particular tool in the collet, right? Which is exactly what it's for. The bluing turned out okay on it as well. I think you'd agree. So I'm happy with that. It doesn't look, I could show you every fault with it. There's a bit of a ripple in one of the bad ripple. There's a ripple there, and I could have done better with that, you know? However, it works. The brackets also turned out okay. This one's for an LED spotlight. It's perfectly functional. It's going to be good as gold, up 10 feet in the air in service where the floors cannot be seen. And the bracket for the filter for the compressed air that drives the new plasma cutter is going to outlast the filter and the plasma cutter and the welding trolley. So I'm kind of happy with that. The ring turned out okay too. Rolling up the ring and getting it aligned, it almost looks perfectly round, even though it's not if you measure it. So there's that. However, this video is not really about build these projects. This video is about you. It's about helping you get from crap at home welding to well above average so that the things you build don't break. We're not going to be building anything critical. We're not going to be building trailer hitches and ladders and gantries and things of that nature. But all of this stuff I've shown you here, it's not kind of mission critical. Lives don't hang in the balance. There's a smorgasbord of these things that you can build at home, and your welds need to be not crap enough so that you can be reasonably proud of what you build and so that it doesn't fall apart. So if you're thinking about buying a welder and you're not yet across that line, I'm going to show you the next steps, like the fundamentals to get you from crap welding, totally inexperienced, zero, to well above average in the least possible time. And ditto, if you've been welding for some time, which could be years and years and years, or it could be you got a welder for Christmas and your welds are crap and it's quite frustrating several weeks later. I'm going to get you from there to above average. You can run beads. People are going to go, dude, you can weld, right? Even though you're not going to be putting the cooling system together for a nuclear power plant anytime soon. So stick with me on that. Today's video is not sponsored, and what's next is 10 actionable categories of things you can do to elevate your welding game. But having said that, if you are in the market for a new car or you want to get rooftop solar to divorce yourself from the horrendous power bills that you will suffer as a consequence of one of the hottest summers ever, which we're having currently in Australia, check out the links in the description because I have excellent teams devoted to both of those things, and doing it this way insulates you from the cowboys and car dealers and sort of solar rip-off merchants and all of that. It insulates you from them and it does not cost you anything extra. Welding at home is harder than welding in industry. It just is. It's harder than being a professional welder. And I know every professional welder who might be reviewing this video so that they can correct me in the comments, I know their heads are exploding at this point. If you work in industry, and I've been in industry, in heavy industry, I've been in welding bays, I've worked in them when I was training to be an engineer. They're set up for welding. It's perfect. The welding machines are awesome. You want to run a 4mm electrode, like knock yourself out, dude. You want to run 1.2mm flux cord, dual shielded wire, 2 thumbs up, piece of cake. You want to preheat the job. You want to do anything. You got carbide burrs to spare for aluminium casting repairs and things of this nature. You've got all the cool tools and the environment is already set up. This is not the case at home. Your welder is not as good as the welders in industry. You don't have the same access to the same range of processes, so you've got to compromise all over town. And the other thing is the dude who's welding for a living, he's doing it every day. He spends, I don't know, 6 hours a day welding or preparing to weld kind of thing. And that really does change the game. The expectations, obviously, in industry are higher because they're building things that do matter. You know, if you're building suspension brackets for GVM upgrade kits for Land Cruisers or patrols or something of that nature, it's kind of bad if they fail in service, isn't it? Lives are on the line. If you're doing pipeline welding, you always have some glorified Nazi of a quality control dude or dudette looking over your shoulder, metaphorically assessing your work, looking for minor defects like arc strikes outside the welding zone, and perhaps we'll have to fail you and revoke your ticket about that because you've done that 3 times this month, right? So the expectations on professional welders are extremely high and the skill set is extremely high, but I would stand by my contention that welding in industry is easier than welding at home, right? You don't have anything to set up, you're more match fit, blah, blah, blah. And that means that this is a properly ambitious thing for you to want to do, right? It's hard to weld well at home. It's hard to do it well. And that means don't be too frustrated if it takes you several weeks to get in the groove. You know, just apply yourself a few times a week to practice. You don't have to build anything, you have to get hood time, right? That's kind of important, but you have to have the fundamentals straight. And that's what we're going to talk about next. If you've never welded before, or if you've welded a bit and your welds are turning out crap, you're probably spraying and praying You know, you got the gear, and we're not going to talk about health and safety in this video because that's a huge topic all on its own. And I've already done Duos videos on that, dude. I will link to them in the description as well. Welding is an excellent way to kill yourself in the shed, either short term, you can do it quickly, or you can do it over time as well, because there's plenty of lingering hazards. The best advice I can give you with welding at home is don't die, all right? Don't die, dude. And those videos can help on that. But if you're spraying and praying, it's really not the way to do it. You've got to realize that the experiment you're running has to change if you want a different outcome. And you have to realize that the outcome of the welds that you do is purely a product of everything you did in the lead up to and including running those beads. So it's down to the preparation, the machine setup, and the technique, right? And mainly now I want to talk about the technique because this is the easiest thing to improve and it's the biggest problem with all home welders. Their technique is shit. They're learning it from other dudes who weld at home who don't know how to weld, and they're applying just crap techniques and getting a crap result, which is hardly surprising. So I'm going to talk about stick welding first and just getting the basics right with stick welding, because it's the easiest process in terms of setting up the machine, and philosophically it's the easiest process to understand in terms of its overall functionality. MIG welding is easier to do perhaps, but harder to understand. So with stick welding, you use these wire electrodes like this that have particular grades, but let's not worry about the grades if we're just starting out. They're all basically the same thing. If you go to Bunnings, you'll be buying a packet of electrodes, most probably called 6013. And in some markets, that's called farm rod around the world, you know. It's got a cellulose electrode and 60,000 PSI of ultimate tensile strength. The thing you have to realise with actually the technique, once you've got your machine set up, and I'll talk about that in a minute, dead easy, is there's 4 things that you have to get right, and you have to get them right all at once. And the 4 things are the work angle, the drag angle, the arc length, and the travel speed. Work angle, drag angle, arc length, travel speed. Say it over and over in your head, dude, because if you don't get them right, your welds will be shit. They'll be shit, all right? So the work angle is like this. Let's say I'm welding this bit of plate to this bit of plate, and I'm doing what's called a butt weld, okay? And this can be an open root butt weld with a bit of a gap, or a butt weld, right? With no gap. So I put this here, and it's sitting down flat on the plate. My work angle, that's 180 degrees because it's flat. My work angle is going to have to be 90. Not here like this, right? Cut the joint in half. If I'm doing a fillet weld, my work angle has to be 45, especially when I'm just starting out. Occasionally you need to tweak this when you're putting thin stock together with thick stock, because you have to tweak your angle to concentrate the heat down on the thickest part, which is the hardest to fuse, right? Because it's more of a heat sink. But when you're just starting out, you get 3, 4, 5, 6 millimeter plate, and you get little coupons of it, you run beads on plates, and then you start doing joints, right? What you should do if you're starting to weld is get a piece of steel like this, clean it up with a flap disc so it's not filthy like this, make it nice and clean, and then just pretend that it's a butt joint and you're running a bead on a plate, and run a bead and a bead and a bead and a bead, and do it until it sucks out your soul, the process, and leaves you devoid of the will to live, but good at running beads on plates. This is exactly what you would do in welding school, or if you're an apprentice being trained in industry, okay? So this is your work angle. It's 180 degrees every time, okay? And you just travel across the plate like this. And when you travel, you drag the electrode like this, okay? You drag it. And you drag it at about 10 degrees. Sometimes with 6013, you might want to increase that angle a little bit. And if you're not getting fusion properly into the whatever, you just turn the current up on the machine. We'll talk about that in a sec. But dragging like this. Now, do it two-handed. elbows in. Welding is a remarkably physical process. It's kind of like boxing, right? When you're boxing and you're throwing punches, you can't do it just standing there like normal people stand where you're about to fall over. You have to activate your hips and your knees and get like you're getting ready, right? Like so you can move. You do this with welding, elbows in, locked in place, comfortable. Boom. Bear in mind I'm left-handed, so if you're a righty, I'm sorry, but just pretend you're looking in the mirror because you'll be traveling in the opposite direction. You'll be doing this, okay? Boom. I only do this under sufferance if I can't fit into the job this way, right? Being able to do it bilaterally is probably pretty useful, but it's harder for right-handed people to do that because they haven't been adapting to a left-handed world their whole life. So anyway. The next thing is arc length, okay? It's very easy because the rod gets consumed as you're using it. It's very easy for you not to concentrate and for the arc length to grow. What you've basically got to do is monster the electrode down towards the joint so that the arc length is nice and short. That's how it's designed to be used, okay? And then your travel speed. Basically, if you're burning holes in the thing that you're trying to weld, you're moving too slow. And if your weld is sitting up there, like not really fused into the metal, if it's a really high bead, like it's just sitting like a, I don't know, you drop a pen and it sits on the desk, if it's looking like that without being flat, without being flatter, then you're moving too fast. Or if you're looking at bare edges of the joint that looks like they've been washed away, that's called undercut. And that's as a consequence of moving too fast. You heat up the edges of the joint, it washes away, but you don't spend enough time there to deposit enough material to fill it back in. So too slow is wrong, too fast is wrong, you've just got to get Goldilocks. So you start with beads on plates, you go run a bead like this and you look at it and you see how humped up it is and you think about how the arc length went on the way through and you think about all these, was my drag angle too steep like this? Was I at my, 90-degree work angle? 90 degrees is this way, drag angle of 10 or 15, something like that. And then counterintuitively, you're moving this way and you're feeding this way. And that does your head in. It did my head in for whatever it was, 35 years ago or something, 40 years ago, when I first did this. It did my head in I still remember it, doing two things at once like this and trying to hold the whole thing steady. You've got to feed in and move this way. And once that clicks, a little switch in your head goes, ah, that's how that works. And then Jedi, right? It just happens. So 90 degrees, 15 degrees that way, short arc, travel at the right speed and just go down the plate, run endless beads, run 20 or 30 a day, 3 or 4 times a week. And before you know it, you'll be doing that fine. You'll be able to progress on to doing joints. You could do fillet joints, lap joints, butt joints, all of that stuff. You can do open root joints, whatever. Welding's awesome because you can have this kind of profane discussion and it's completely legitimate. You can be talking about laps and butts and open roots and penetration all day long without having a meeting in the HR department about your conduct at work, right? So It's not exactly plumbing where you can talk about cocks all day long. Where did you stick that cock kind of thing. But on the pro side for welding, you don't have to get down into a septic tank and unblock it ever. So there's that. Okay, let's talk about MIG welding now, which is almost the same. The same processes and physicality pertain to MIG welding. The only difference is you're feeding the wire out of the gun, and it's more complex to set up the machine, which we'll get to. Same sort of thing with MIG welding in terms of the joint angle and the work angle. And then you've just got to get the travel speed right. Instead of getting the arc length right though, because the machine is pushing wire out, you set it up to push the wire out. It comes off a dirty big spool and it just goes as long as you press the trigger. It'll just feed wire endlessly. So instead of the arc length, you've got this thing in welding school that they call CTWD, contact tip to work distance. The contact tip is the thing inside this shroud that the wire comes out of. This is the contact tip, okay? And it is the electrical contact for the, in this case, positive pole of the machine. When you're doing gas shielded MIG welding, which this is set up for, your table or your ground clamp is negative and that's positive. And then you cause a short circuit that makes the welding work. Polarity changes if you do gasless MIG. We'll talk about the machine in just a minute, but contact tip to work distance means how far away is the contact tip from the work, and it's got to be really close. It's got to be like ideally 10 millimeters away, which is 3/8 of an inch in America. Okay, so you've got to be right down there on the job, right? Boom, right down in there. Not like this, because if you do this and you're a long way away, you've got much more wire between the contact tip and the job, and it changes the resistance. And then it changes the arc characteristics and your welds will be shit. When you weld for the first few times, what happens when you're doing short circuit MIG, which most home welding is, okay, there's a few different processes. There's spray transfer and globular transfer, and you can have pulse on top of that. But most basic MIG welders for home do basic short circuit MIG transfer mode, all right? And what that means is the wire comes out, touches the job and goes bzz, and then the voltage burns it back. Repeat about 100 times a second, which sounds, if you get it right, it sounds like bacon frying on a hot pan. If it sounds like that, nice and consistent, no machine gun sputtering, boop, 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 then you've got everything right. The machine's right and the contact tip to work distance, which you could call stick out, right? They call it the contact tip to work distance in college, and then on the shop floor it's stick out, right? You've got to get your stick out right, which means, because the contact tip is way inside the shield here, it's about 2 or 3 millimeters inside. That means you've got to get this sort of 6 or 7, 8 millimeters maximum away from the joint. And that poses a challenge because it's hard to see exactly where the wire's going. You've got to get your head around to the side while you're doing it, because you've got to inject the wire right down into the root of the joint, not off to the side, right? That's kind of important. Same with stick welding. You've got to be right there in the joint, although much easier to see because much less equipment in the way. So there's that. Contact tip to work distance and then travel speed. And in practice, with all welding, the machine only has to be set up in the ballpark because the welder, the person, the human, can accommodate the settings on the machine if they're a little bit off. Most professional welders don't end up making 10,000 adjustments to their machines every day. They just change their travel speed when they move from stock thickness A to stock thickness B. So if the machine is set up a bit cold, just travel a bit slower, right? More heat into the job, good enough, okay? Machine has to be in the ballpark. Same with stick welding, right? If it's a bit cold, just travel slower as long as you can maintain the arc, right? If it's a bit hot, vice versa, travel faster. There are limits on this process. The machine has to be in the ballpark. So my advice to you if you're stick welding and the machine setup is you only have to get the polarity right, meaning in most cases the electrode has to be positive. So the gun you're holding is the positive side, and wherever you put your ground clamp, that's negative, okay? The job is negative, if you like, and then you short circuit it. Read the packet that the electrodes come in, and it'll have an amperage range. It'll say 80 to 110 amps or something, okay? So then go over to your machine and just turn it up to 110. A lot of cheap machines are very ambitious in the claims they make about the amperage that they're delivering. So 110 might only be 90. So that's why I'm suggesting you start high. If you can't maintain an arc, then turn it up a bit more, all right? And if you burn through the material, turn it down a bit more until you get to the point where you can match your travel speed to the deposition rate, the rate at which your electrode is being consumed, and get a decent result. Now, MIG welding is more complex than that. It's harder to understand because there's more things to set up. In the case of so-called gasless MIG, which is really flux cord arc welding, you don't have to worry about the gas, but the polarity is different, okay? The torch is negative. They call that DCEN for DC electrode negative, okay? The job is positive, and guaranteed if you're trying gasless MIG and there are just BBs and weld spatter everywhere and the joint looks shit, the first thing to check is the polarity, because that's typically characteristic of having the polarity reversed. If your gasless MIG is positive here, you can't do a decent weld. You just can't, okay? The other two controls that you need to set on the machine are the wire feed rate and the voltage. The best thing there is just open the flap where you load up the spool of wire, and there'll be a table and it'll say this thickness of wire, this thickness of material to weld, this voltage, this wire feed rate. So just set the machine on that. And if your welds are turning out crap, it's not on the machine, it's on you. It's something you're doing. It's work angle, travel angle, CTWD, stick out, travel speed. It's something to do with your lack of consistency there, okay? Quite often with MIG welding, what people do is they start here like this and then they end up here like this. And what happens then is that you're blowing your shielding gas away, and towards the end of the weld looks shit, right? So you've got to be reasonably upright so the shielding gas stays on top of the pool, okay? Another typical problem with MIG welding when you start is that the wire is being fed out and touching the work, and it tends to have a certain push back. So you can start nice and tight with your stick out, but find that towards the end of the bead, you're back here and your welds are comparatively shit, right? And that's why you just run endless beads on plate, because you can deal with all of those problems. You can run it back in your head and say, oh yeah, with that one, that's good at the start and terrible at the end. What changed, okay? And it's usually something like you started here and you started here and you finished there. And that's never going to work, all right? So you have to be more of a CNC welding robot. If you want to see a human CNC welding robot in operation, have a look at Curtis from Cutting Edge Engineering. He's the closest thing to a human CNC robot that I've ever seen. He's bloody good. So many of his videos, particularly where he builds up, you know, the ends of rods and eyes and things of this nature on big earth moving equipment, where he uses the dual shield wire to build up those items. He's extremely consistent. The guy is a freaking borderline robot. So that's Cutting Edge Engineering Australia. You want to watch that channel. You see some A-grade pro welding in that for sure. Okay, so basically what I'm suggesting here is that just get the machine in the ballpark, practice over and over, run it back in your head and get lots of hood time. And then just get those four things, right? The two angles, the stick out or the arc length, and the travel speed. Just tweak them a little bit, one over and over and over until it clicks and you go, Jedi. Welding is, philosophically at least, really like painting. It's more to do with the preparation than the actual painting, right? Like the hardest thing about painting 20 metres of old handrail, balustrade, whatever, that's been rusted, and it's metal, so it's rusting and the paint's flaking off. The hardest thing about painting that is not painting it. It's the preparation. You've got to scrape it back. Then you've got to sand it. Then you've got to do primer. And then you get to make it look sexy by painting it. And welding is really like that, because the preparation is absolutely key. If you're trying to weld together two things and they're rusty and they've got 4 layers of old paint on them and they're covered in grease, it's not going to end well, right? You can't get that to look good. If you're going to try and butt weld these two bits of plate together just like that, it's not going to end well. You need to grind bits away. You need to put bevels around the edges so the weld's got somewhere to go, because this black stuff on the outside of hot rolled mild steel, which is the most common material that you'll weld at home, that's not metallic, okay? That's an oxide that is formed when the steel is hot and comes into contact with the atmosphere, and it's more crystalline than metallic, all right? And it's a bastard. It's full of impurities. It requires more energy to burn off, and then it gives you inclusions in the weld because it's full of impurities. So you grind it away, you bevel the job, you shine up around the zone that you're going to weld, and then you bevel it away so the weld's got something to go down into and penetrate, because welding is not glue, it's not Sikaflex, it's not frickin' epoxy, it's fusion. You have to melt the metal, preferably all the way through in many situations, so that the strength of the welded part is not dissimilar, much weaker than the strength of the underlying material itself. So when I did a lot of this stuff, notably the Franken wrench, I set this up as an open rooted butt joint. All right, that means there was a gap between the handle blank and the cut-off end of the wrench, and it was beveled all the way around so that when the wire goes in, it fuses at a deep level without any defects. Now, there's no filler in this, and you can't tell exactly where the weld is. You can't see any cracks around where the weld is, where the fusion was incomplete, and that's because I took great care to do multiple passes there and over-weld the whole thing and make sure there weren't any voids. If you want to see a defect where there are cracks, where this didn't work out properly, I've got one here. Here's one I prepared earlier. You can see, where is it? I need a pointer, this will do. Just here. That's incomplete fusion right there. Now, I did everything right in the preparation and just blew the welding for that. I didn't get proper fusion right down into the joint. It really doesn't matter in this case because this is only something that sits on the floor, and it only supports about, the 4 of them support about 600 or 700 kilos worth of milling machine, so it's not carrying a great deal of weight, and it's not subjected to a whole lot of fatigue style loads. It just sits there, so I'm going to live with that. I could fix it by grinding it out and going again, and if it fails, that's exactly what I'll do. But you've got to sort of engineer yourself for complete fusion through the joint. A common way of doing this is to tack the thing up first, right? Everyone's heard of tacking, and I want to just run by tacking with you because it's such a fundamental part of the process, but also it's so fundamentally misunderstood, right? And let's just say that I want to weld these 2 bits of steel tube together. This is square section steel tube. It's 25 by 25 and 3 thick. All right, if I want to weld that together like that, that's a very common thing for the home welder to do. I would tack it in each corner. I'd tack it specifically on each corner as opposed to in the middle of the flat faces. And I do that for a reason, okay? The reason we're going to tack something to start with is because when you weld, the weld pool pulls towards the side that you weld when the freezing takes place. Now, freezing meaning going from liquid to solid, not getting cold. All right, it's not going to be cold, but it is going to freeze. So if I just weld down this edge here, for example, then this is going to freeze and pull the joint this way. You can try it at home if you want. Just do that. Just unsupported, just run a bead of weld along here. And you'll find that if you set it up at 90 degrees to start with, it's going to be over here, much less than 90. And if you don't compensate for that in some way, then that's potentially going to ruin every product that you ever put together. And my strategy here, tacking is something that you do strategically. It's a clamping system. You fixture your part together. You use something, it doesn't matter what. You can use a piece of angle line if it's at 90 degrees. Not all angle is that accurate. But you can get a square like this and clamp the part together at 90 degrees. So it is fixtured in place, right? You just put a couple of clamps across it, it's fixtured in place. What do you do then? You tack it. You put a tack in each corner, right? And those 4 tacks hold the product in place while you weld it together to prevent it just pulling, because you've got opposing tacks when you weld this bit. The reason you tack in the corner is because that's where your welds start and finish. If you tack in here in the middle of the face, then as you weld, you've got to go over your tack and it'll make your weld look shit. And there's also a problem where you end your weld. So if you start here and you end here, you got to dwell around here a little bit if you want this bit of the weld not to look sort of hollow and cratered out. And you can compensate for this problem to some degree by having a tack to finish on, right? That's kind of cool because you don't have to worry so much about filling in the end of your weld by dwelling here for a little bit longer. It's not as much of a challenge if there's already a tack at the end point to fuse to. And there's no law that says you have to make welding difficult. You have to make welding as easy as it can possibly be. So the strategy is tack on all 4 corners. I'd tack on this corner, then that corner, then that corner, then that corner. So I'd do it diagonally because a tack here has the potential to pull towards that tack. And then when you tack on the other side, it'll pull back and it'll be fixtured in place anyway. And it's a small amount of weld, so the actual pulling is quite reduced, minimal, right? And then just do the other diagonals. So yay. And then you weld it out, okay? You weld this bit, then you weld the opposite bit because this will try and pull the other tacks this way and welding the opposite bit will pull back. And then just do the remaining 2 in the same way, okay? That's a sensible way to do this to minimize distortion. And if you're wondering about tacks and how strong they are and welds and how strong they are generally, this is a rabbit hole that we should consider because many people, particularly home welders, tend to overweld the crap out of everything they build. If I do a tack and it's quite a small tack and it's only 3 millimeters by 3 millimeters at its sort of thinnest point in cross-sectional area, then that's about 1/8 of an inch by about 1/8 of an inch. And 1/8 times 1/8 is 1/64 of a square inch, which is in the ballpark, 1/60th of a square inch. And I'm doing this in imperial for a very important reason, because this electrode, for example, is 60,000 PSI of ultimate tensile strength. 60,000 pounds force per square inch of area. And if I've got 1/60th of a square inch, I've got 1,000 pounds force of tensile restraint capability before it fails in pure tension, okay? So if I said one tack was about 1,000 pounds of ultimate tensile strength and divide that by 10 for a factor of safety, that would give me about 100 pounds force of clamping effort, which is about 45 kilos. And if I do 4 of them, that's 400 pounds force, which is about 180 kilos of clamp. And I think you'd agree that if we were welding these 2 bits, if I can find bit number 2, wherever I frickin' put it, it's probably hidden in plain sight somewhere. There. If I'm holding that together with 180 kilos of clamping force, that's a pretty good clamping arrangement to weld it out, right? 180 kilos, that's 3 strippers pressing down, holding this joint together. That's, to me, just makes my head explode. So another thing to mention here is galvanization, right? Because a lot of common steel extrusions come galvanized. Galvanizing is very dangerous. And I know I said I wasn't going to talk about OH&S, but this is such an easy thing to overlook. It warrants discussion, okay? Grind the coating away with a flap disc because The zinc is poisonous. It can give you an allergic reaction called, that welders call metal fume fever. You can Google that for more. But it makes you feel as sick as a dog. And that's not the worst of it, because galvanizing, the zinc coating also has a little bit of lead in it. And when you subject that to the arc, it forms lead oxide, which is linked to brain cancer. So don't weld galvanized material without removing the galvanizing. Another way to remove the galvanizing, if you've got time, is to just put some vinegar in a plastic container and then sit the end that you want to weld in that, leave it there for a couple of days. The acid in the vinegar will eat the zinc and will leave the steel behind. And that's not a bad way of doing it, particularly if you're just doing a whole bunch of joints on the end or a whole bunch of miters with another miter here, right? You can just sit all of those in vinegar and come back next weekend sort of thing and weld it all out after just washing it out with fresh water to neutralize it a bit. So that's exactly what I did with this bracket. You know, it's galvanized and it's going to be used outside to support an LED spotlight. And I had to get rid of the galvanizing to weld it because I'm buggered if I'm going to breathe those fumes. You've got to be kidding. The other thing I do about fume management, incidentally, and it's running now, you might be able to hear it just quietly in the background. My second biggest fan, so loyal, always in the back there, always blowing across this way. And a big roller door here, it's like 5.5 meters wide and 2.5 meters high or something. So there's a big opening here and a fan blowing here. Of course, fans and gas shielding don't go together, so I always try and weld a bit here like this so that I block the breeze, but the breeze wraps around me and picks up the fumes. The breeze is not strong enough to get rid of the gas shield, especially when my big fat slobby self is in the way. So there's that. On the issue of you and welding, I'd suggest two things here. The ABC of welding is always be comfortable, right? The minute you get uncomfortable, bad shit happens. You're not as steady, right? Because you're over here like this and one foot's in the air and you're falling over, and you know, welding is already like riding a bike, only the bike's freaking on fire in hell and Satan's running you down in his S-class. You don't need the compounding difficulty of being uncomfortable. Leave that to the pros who have to climb through ducts and weld, and you know, they have to sometimes in industry, they actually put a strap on the welder's ankles so that if they lose consciousness, they can be pulled to safety in these demanding situations. Or, you know, it's very difficult to weld in industry, not as hard as at home in some ways, but you can afford, generally, doing the kinds of things that home welders do, you can afford to be comfortable all the time. You can see in these shots that I have this block. It's always sort of floating around here because it's an elbow rest. You can use it to stabilize everything. Stability, very important, right? Do a dry run before you press go. And in fact, I blew that a couple of times. I didn't do a dry run and I paid the price, right? And I should have known freaking better, frankly. But, you know, I can set it a bit lower. I can put it up here so that if I'm welding down on top of something, I can get up here and I can be comfortable. The other thing about always being comfortable is there's no law that says you have to be an ace practitioner of vertical up and overhead welding. Vertical up is really hard to do. It's technically challenging. You should try it after you get reasonably good at welding, but you don't have to do a vertical up weld just because the piece is sitting there on the plate like that. Change it to horizontal, do that, flip the part, right? You don't have to do overhead. Just turn the part over, put it down like this, weld it like that. Do it as easy as it can be done because your welds will be as good as they can be, and that's what you're going to be judged on, even if you're the only one doing the judging, right? You'd always be comfortable. Now, I'm just going to check that I got all of this stuff. Ah, yes. Dry runs, and make sure you can see. All right, dry runs. I'll show you what happens when you don't do a dry run. This happens, right? I freaking hate that. See me going off course there? Retrospectively, you can see that. That's like forensic evidence, isn't it? You can look at that and go, he really wasn't lined up there. And that's because A, I didn't do a dry run. and I lost track of where the joint was because I couldn't see it in the literal heat of the moment. Compare that to this one. I did a dry run and I could see it. Like, it makes a big difference, okay? And likewise, here I painted myself into this corner when I did these plug welds on the back of the feet for the milling machine. And the reason I painted myself into a corner was I lost track of where the edges of the holes were. I just couldn't see them anymore. So I was spraying and praying, which I freaking hate. And I knew I was doing it in the moment. And some of the raw welds were just embarrassingly terrible, the way they didn't conform to the hole and all of this stuff. So I should shoot myself or slap myself profusely off camera, perhaps. That's probably against YouTube's terms and conditions to do that on camera, especially if you enjoy it. But I should berate myself for doing something like that and losing orientation on exactly where I was. So you've got to do a dry run, and part of the dry run is so you can do the biomechanics of exactly where you're going to run the joint. If I'm going to run a joint down here and it's going to go all the way along there, I want to do that dry run. And the second thing I want to do is I want to look around here and I want to go, yeah. To get the wire right down into the root of that joint, I've got to be there. And here's my angle, and I'm setting all that up. And then I'm getting the biomechanics of the start and the finish. Start, finish. There's no law that says you don't have to do 3 or 4 dry runs if you want. And guaranteed if you do that, your weld is going to turn out much better than if you just kind of walk up and go like that. Because then you'll be looking at something where you go, could have done that a lot better. And you're always going to be saying that to yourself about the welds that you do. Point number 4 on all of this is grinding and where it fits in. There's a school of thought that says that grinding is a mechanism that compensates for shit welds. And really it doesn't. Like, aesthetically, maybe a little bit. But if your weld is shit because you didn't do the preparation, you didn't bevel the joint, and it looks like chook shit on top, the only one of those problems you can solve by grinding is to take away the aesthetic problem. If your weld is still terrible, it's not going to be strong enough potentially, and grinding doesn't fix that. So grinding is kind of part of the process. It's not a compensatory mechanism for being terrible at this, except in a purely aesthetic sense, all right? So I did a bunch of grinding here. I did a couple of tests, and I figured out I liked grinding the feet better than turning them on a lathe, although I did set them up in a lathe and knock these corners off and put a bit of a chamfer on them here because it's so important for them to look good because they're the feet on a milling machine sort of thing. I also took great care to over-weld the crap out of this so that there wouldn't be any voids when I finished the part. And that meant I had to remove a lot of material, so I got a nice coarse disc on my belt grinder and I knocked that down to the point where I could hand finish it. I'd advise you strongly not to grind finish things of this nature because it's so aggressive. You know, you probably use a flat disc on an angle grinder. Most people don't have a belt grinder off the bat. They're using a flap disc to do this kind of gross material removal. And the perverse thing about machining and grinding is that you can always remove more material, but it's bloody hard to put it back if you go too far. So a project like this is kind of interesting because when you get it fully welded and it's over-welded by design, right? You look at it in that state and you think, Jesus Christ, this looks terrible. Right? And then you start grinding it to remove the gross over-welding, just to get it back to the point where you can hand finish it. And you go, oh, yeah, that might look okay. And then you whip out a set of hand files, which many people in the DIY space probably the last time they picked up a hand file was 1985, right? But hand filing is a really good way to ensure that you don't remove too much material with a super aggressive grinding disc. And I hand filed this, and I got it hand filed, and I use those little die files to get into these curves and things of this nature, and it turned out okay. It's not perfect. And then when you finish it with this gun blue stuff, Birchwood Casey gun blue, which requires you to clean it with acetone and brush it on a few times and soak it in oil overnight once you've got the blue coating established. once you look at that, you think, yeah, that was all worthwhile. But in the middle of the process, you're thinking, Jesus, how am I ever going to resurrect this with my dignity intact kind of thing? So don't be demoralised halfway through. Grinding's part of the process, but it's not a compensatory mechanism for being crap at welding. I'm not going to bother grinding any of this because it's sitting on the back of a welding cart. I'm just going to give it a light sand and paint it black, right? This is the bracket for LED spotlight, and I'll show you. So the bracket goes into the wall, right, which is masonry, and then the light, these are drilled and tapped for M6 by 1, and it compensates with the 2 slots and the hole in the back of the light. So the bracket's on the wall, the light is bolted in. The reason it is at an angle like this, that's carefully done by design, it's because the light is on the corner of the house and I don't want the spotlight to illuminate half of the neighbour's yard because that'll piss them off and it won't be very effective at illuminating mine. So hence the angle, right? I am going to grind these welds back just for aesthetics, okay? But they're good enough. They penetrate enough. They're strong enough. So I am doing it on a purely aesthetic basis there. I'm not going to worry about this, which you're still scratching your head about, but I have used a carbide burr just to take a few of the welds down a little bit, just to make them look, you know, vestigially nicer. I ground the other Franken wrenches a bit, but the intrinsics of the grinding process there detracted from the aesthetics of the job, and I'm not happy with it. So that's where grinding essentially fits in. Point number 5 is only for you if you're thinking about buying a welder, okay? There's 2 strategies here. If you're not sure that welding is right for you and you're not sure that you'll end up doing very much of it, you might end up hating it, buy the cheapest welder you can, okay? And if you're welding thick stuff, like anything from 3mm and up, buy a stick welder because you get a cheap stick welder for $150 easy, right? And it'll do the job. It'll run these little 2.4mm electrodes and they're going to be fine for home work. If you go up to the next level of stick welder, you can run the next size electrode, which is 3.2, which is kind of more versatile for heavier plate. But realistically, most of the work I do here, if I'm doing stick welding, I run 2.4mm electrodes. And that means you could get away with a very cheap welder. And that means if you hate it, just put it in the bin, who cares? Sell it for $10 or $20 or something to a friend, who cares, right? Or just give it away. It's not going to be a disaster if you do that. If you're doing thinner stuff, gasless MIG, flux cord arc welding, it's never going to look as good as gas shielded MIG, okay? But it is quite effective. And the flux processes are very compatible with welding outside. So if you're a farmer and you've got to do repairs on location, the flux processes are really good, okay? Because MIG, gas shielded MIG welding, GMAW, gas metal arc welding, and TIG, not very compatible with welding outside because then there's the slightest breeze, it blows the frickin' gas shielding away and it renders the process useless, right? So the flux processes have their place. And there's a lot of snobbery in welding too, I'd have to say. You can get a decent result with stick welding. It's going to take a bit longer because you can only weld for this long until you've got to stop and put in a new electrode and go again. And you've got to chip because the flux melts, sits on top of the molten pool, prevents access to atmospheric oxygen and corrosion, oxidization of the molten metal, which it's quite keen to do in its liquid state. And then it produces slag, which has to be chipped off and then wire brushed, or in the case of flux cord MIG welding, you can usually just wire brush it off, but it's quite a messy, smoky process in both cases, right? But it'll get you started. And if you can weld outside, do it outside so you're less exposed to the fumes from the flux. But that's enough to get you started, all right? And you can weld thinner stuff down to probably 1.2mm thick, maybe 1mm thick with spot welds, with flux cord arc welding. So gasless MIG, same deal. So that's basically what I would do there. I'd buy the cheapest gasless MIG on the market and that would be cheap because they didn't put the gas functionality in the machine. I'd run a little spool, one of those, whatever they are, 1 kilo or 900 grams or something. And the only thing about gasless MIG that I'd suggest is if you wanted to do multiple passes on a thicker job, you've got to get a welding wire that is compatible with this, because the cheapest gasless MIG wire is not compatible with multiple passes, right? Just something to bear in mind. So what's the other option? The other option is you buy a multi-process machine, which is the machine I'm using. It's got stick welding, it's got gasless MIG functionality and gas MIG functionality, and some TIG functionality. But realistically, for the multi-process machine you want, it's going to cost you $1,500, and you'll need a 15 amp plug in your workshop to run it. At least you do for that machine that I'm using, which I'm very happy with. It's a Unimig Razor 205 Smart Set, and it's been really good, totally reliable. I've never had it trip out for overheating, and I have welded on some spectacularly warm days and run a lot of beads kind of back to back. So it seems pretty robust for a home welder, and I'm extremely happy with it. But the price of acquisition is significant, and if you're not sure that you want to be a home welder, then that's going to be a bit of a financial disaster if you end up with a $1,500 sort of red herring in your shed. You do need some basic stuff as well. I know you can get an old school style flip-up welding helmet for about $15 these days. They're terrible. I learnt to weld at the tender age of about 19 or 20 using them. Everyone was using them. They just started. This is like in the early 80s, I'm going to say. They just started with auto darkening helmets, and they were horrendously expensive. And in the factory that I was working in, only the most experienced welders qualified for an auto darkening helmet. The rest of us are doing this, right? Doing this is hopeless. It's terrible, okay? It can be done. Everyone used to do that. But a helmet like this is $89 at Trade Tools. Now, I know I've got the little Trade Tools football up here. They sent it to me the other day. I'm not sponsored by Trade Tools. I just buy a lot of stuff from them. And a helmet like this has relatively clear vision. Like it's really good for the price for $89. It's got a big viewing area. You can see the viewing area. And the plastic it's high quality plastic. You're not going to crack it, you know? The reason I advocate helmets like this, as opposed to this, is that you can be fully set up, both hands, dry run, ready to go. And you don't have to take a hand off and do this and lose your orientation and then figure out where you are when it's totally black and when you flick the visor down to welding mode, okay? That's hard. It's probably good for the soul. I found it so liberating the first time I got an auto darkening helmet. I went, how long's this been around? It's awesome, right? And they're so cheap now. The other reason is because it's much harder to flash yourself. Welding produces infrared radiation and ultraviolet radiation. In fact, it's worse than the sun on UV because the upper atmosphere attenuates the UVC, which is the most highly carcinogenic frequency of ultraviolet radiation, okay? And you don't want to be exposed to that, and yet every time you strike an arc, you're bathing in it. So you have to cover up. I know I said I wasn't going to talk about OH&S, but the equipment, get an auto darkening helmet because you can't flash yourself, right? When you look through one of these, and essentially, I hope this works, essentially this is what you see. You know, there is a clear window in there somewhere. I can kind of see you, but there's polarization. So you might not get a clear view of that if you've never looked through one, but it is really clear to look through. The clever thing about these, though, is that they're already blocking all of the UV and they're already blocking all of the IR, right? All the infrared. Infrared can cook your eyes. UV can damage them by giving you ultimately ocular melanoma, which you don't want, right? Those frequencies are blocked totally. So even if the auto darkening feature fails spectacularly, the only thing that's going to come through is the visible light. It's not going to be transparent suddenly to infrared or ultraviolet because it's got filters, they're hard filters, built into every auto darkening helmet that blocks the infrared and the ultraviolet. And therefore, even if you strike an arc inadvertently, you won't be subjecting your eyes to those more dangerous radiations. So auto darkening helmet these days, not negotiable, is $89. It's a freaking no-brainer. If you've got the bucks, following on from what we just talked about with machines, get a MIG multi-process machine. If you possibly can afford it, you're thinking about going that way, get it with quote unquote synergic functionality, SYNERGIC. And this is a scary big word, I suppose, but really it just means you get R2-D2. You get to fly the X-Wing, R2-D2 gets to look after the technicalities. And the clever thing about synergic mode is that it puts a little computer into the welding machine, and the computer listens to the MIG, right? You tell it by flicking a switch in the case of that machine. I tell it that I'm using 0.9 millimeter wire, which is 035 in America. And I tell it what gas I'm using. In this case, I'm using a gas called Argo Shield Light, which is CO2, argon, and a little bit of oxygen, okay? And it goes, yeah, okay, right, noted. And then I start welding and it listens and adapts, okay? And it adapts because the computer goes, what inputs am I getting? What outputs will I deliver? So it tweaks the voltage and the wire feed rate depending on what I'm doing. And my job is to not fuck with it, like not mess with its head and gaslight it by, you know, changing the stick out ridiculously or doing any of this stuff, because Luke and R2 are a team. Luke never fucked around and gaslit R2, so you shouldn't do that to your synergic MIG either. But I just weld consistently and it goes, yeah, I'm feeling it, baby, you need this. So for this whole job, from this thin stuff like this that I welded to these multi-passes on the Frankenwrench, I didn't touch the settings on the machine at all, right? I figure that Unimig has 100 qualified welders there and a few IT guys who go, right, in this situation, here's what we need. And they develop a whole table, not unlike the way a computer in a car delivers the fuel to the engine based on the prevailing conditions of load, like throttle position and RPM and things of this nature, okay? It's doing exactly that. It's just going, yeah, I'm feeling it, baby, you need this, right? And 100 welders and a whole bunch of IT dudes have done that. So why not take advantage of that? Because the alternative is tweaking the settings endlessly when you switch from this to this, and then you go back to this. And then you've got to weld a really thin thing into a really thick thing. And then you've got to weld the same sort of challenge, thin to thick, and then thin to thick. And, you know, it just does your head in doing all this stuff. What setting do you do on the machine based on its table if you want to manually set it, when you've got something so thick and something so thin? And where do you draw the line? The other thing is, if you decide that R2 is coming in a bit hot, then you can just walk over to the machine and tweak it down a little bit. You basically just twirl a knob, leave it in synergic mode, twirl a knob and cool it off a bit. This is kind of helpful if you've got to suddenly weld a little bit up here. Welding overhead is more difficult than welding down, partly because gravity affects the weld pool and it wants to fall out all the time. And particularly if you're using a thing called ER70S6 wire, S6, the silicon is higher, the silicon content in the wire is higher, and it makes the steel more fluid in its liquid state. It's kind of wetter, so it wants to slop around a lot more. If you're welding vertically up or vertically down, typically you want the settings to be fairly cold, in the ballpark, but fairly cold. And if you're doing that, you don't have to leave synergic mode. You just tell R2, by twirling his knob, so to speak, to come in a little bit cooler. And then you adapt and R2 has a listen, and it's a beautiful partnership. you have to learn and adapt continuously. Like, I've been welding for more than 40 years, which does my head in, because in my head I only feel like 25 or 30, but that's really scary to me. But every time I weld, I learn something. I learn something about the last weld so I can adapt it to the next weld. And that's kind of exactly the case here, where I went off course and I had to figure out how to get on course. So imagine if you were doing that in a welding bay and this was a part that you were putting together 300 times. Imagine how good you would be after doing that 300 times. Imagine how brain dead you'd be, because you'd stop learning at about part number 50 and then you'd just be a robot all the time. Another great example of that is this bracket. Now, I can tell you just by looking at it that I did this one first, right? Because it's a bit cold. It's humped up. And I looked at that and I went, you know what? That's a bit cold. And the change I made, I adapted to that by just going ever so slightly slower on this one. And you can see that it just fills in a little bit better. Now, this joint was kind of carefully worked out. I set it up in this fixture square, which is a great tool, but you don't need one of those. You just find yourself a bit of angle, steel angle, that is at or about 90 degrees. And you can do exactly this without spending the big bucks at Fireball tool. Although if you do have the big bucks, these things are very nice to use, I have to say. If you're doing it a lot, they're very nice to use. So I set this up. Most people would weld the joint kind of like that, right? They just weld over the top, or they bevel it a bit and then grind it back, which is okay, I guess. There's no law that says if you don't want to spend 3 hours on a grinder beveling everything, just set it up like that. And then you've already got this perfect 90-degree V-groove to weld down in, and you will ensure that the penetration is complete on both sides of the joint. And then if you are a bit humped up on top, just grind it off and it will look very polished indeed, and the strength will not be diminished. So I set that up in exactly this way. So this weld that you can see humped up here is also down into the V, and there's reasonably good fusion, but I could tell it was a bit cold. So I went slower when I did this one, and here's the result, right? I hope you can see that. With this one, there's a whole bunch of incipient penetration just coming through in the root of that joint. And that's what you want to see ideally. When it's a bit cold, you don't get that. Like, I'm nearly there and it's going to be strong enough for this job at least. But if it was a critical component that you were using for something that mattered, then this part would be in the bin and some instructor would be talking to you, having a stern chat about get your shit together, okay? That's the difference between welding at home and welding in industry. You can have something that's technically a fail, but because its application is not critical, you can kind of get away with it. I guess the broad point is you've got to look at your last weld and critically assess how it is so that your next weld is better. Repeat. I know I've been talking about this bracket a lot, but point number, whatever we are, 8, is about prototyping, because this is the curse of DIY everything. You're always building some frickin' prototype, and prototypes suck. You know, I'll give you an example. This is my first prototype Franken ghetto tap wrench kind of thing, right? And it's perfectly functional. I just cut up an old wrench that I had lying around and cut up a bit of flat bar and drilled and tapped it so that I could hold the tap in a few different ways, and I experimented with that and it's fine. But it looks like a piece of shit. The grub screws are the wrong length because that's just what I had lying around, and it works great, okay? But it's hateful to look at. So this is go number 2. Go number 2 at prototyping, and the grinding. The grinding you've got to do to make it reasonable really just ruins the concept that I had in my head, even though this is perfectly functional. I've used this wrench a few times now to tap and chase a few holes, and it works just fine, but prototypes suck. They sometimes take 5 or 6 iterations till you get to a slick product. This is a prototype, but I really thought about this and I spent a lot of time finishing it. And the next one will be better, but this is good enough, you know? But you're always building a prototype. And with this bracket, same deal. I only had this piece of material, and the offcut for producing this, produced these two tabs, and kind of that's what I had. And I wanted it to be galvanized, and I didn't want to try and find a piece of galvanized whatever because I already had this on hand. So I had one shot at this, and therefore I did the first version in CAD. And I don't mean freaking Onshape or Fusion 360 either. I did it in cardboard aided design, right? Cardboard aided design is really powerful if you're building prototypes all the time, because it allows you to visualize the product in three-dimensional space, and you can reconfigure it. Like, do I want the mounting tab up or down? When it's in CAD, I can have it down and I can think, how's that going to look on the wall, right? Looking at it up on the wall, I'm going, how does that look? Or do I want it like that? And frankly, I want it like that, because with the spotlight in place, I won't be able to see the tabs to mount it. So it'll be a neater job. That's just a really simple example of how visualizing it like this can improve the version that you make, like the proper version. So go from cardboard aided design to metal prototype 1, good enough. I'm probably going to round the corners off a little bit just to make it look softer and neater, you know, but I'm happy with that either way, and it's certainly strong enough. So I'd suggest that if you possibly can, if you're not sure, and aesthetics matter, particularly if aesthetics matter, but also functionality, you can get to prototype 2 being the first one that you make in the flesh in metal if you just use the high-tech miracle of your cardboard aided design. I wouldn't underestimate the power of that and how significantly better it will make these one-shot things that you make. Like if I'd made this out of metal the first time, I might have just decided to do it this way with the tabs down and this piece flipped, and then I'd look at it every time and go, you freaking idiot, why didn't you just put the tabs on top? But thanks to the high-tech miracle of cardboard aided design, the tabs are in the right place, and I'm further down the prototype track, even though I've only made the one part. Okay, tip number 9. This is really just a bit of advice about what to do if you're down the track and you've done all the beads on the plates and you've set up all these fake joints and you've just welded them, and that process has been so long and so arduous, and it's sucked out your soul and left you bereft of any will to live. If you're there and you finally think you might like to start making something, what are you going to make, dude? Probably not a set of feet for your milling machine unless you really need that. You can certainly do that first, it's not that hard. But if you just want to make something and you want it to be cool, I suggest you make one of these, okay? This is like an apprentice who never complains, never takes his mind off the job. He's rock solid, dude. He does one job and does it really well and never says, can I go and have lunch yet? You know, kind of thing. What is it? This is called a welder's third hand, and it's got one job and it's really good at it. So let's say I've got this widget here and I want to weld that tab to it, right in the middle like that. And I've marked it out with a line, and what are my options, right? I can hold it here in my hard to use heavy glove and tack it, but I can't really hold it like that because I want to tack it at the ends, and that's right where my fingers are, and I'm going to burn my fingers and put a hole in my gloves. So then I'm going to have to set it up like this, and I'm going to have to try and hold it like that, and it's going to pivot like that, just pivoted there. It's going to freaking suck, dude. It's terrible to do this kind of thing. These little fiddly bloody welding jobs with tabs and little things, nuts and bolts that have to get welded to parts and all of that kind of crap, okay? You just get your welder's third hand, and this is a bit of a cluttered surface, but boom. These things always work. They never slip. They're just, it's almost impossible to get them wrong, okay? And you can build them out of any scrap crap that you've got lying around. And if you haven't got any, just go to the local scrap metal merchant and go, oh yeah, I can use that and that and that, and like $15 later, you've got the material to build a welder's third hand. And they're really versatile too, because if you've got the same thing to hold, albeit at a greater sort of elevation, it's compatible with that also. So it takes almost no time to set this up. And then once it's set up, it's just, you've tacked it in place. You check it for square, you nudge it around, get it exactly where you want to get it. Like you can easily nudge it this way for square. Welder's third hand goes off and has a coffee. You weld it out. Beautiful, okay? The other beauty of this is that some parts that you make, there's a very low tolerance for flexibility in the design, because if you get too flexible, the part just won't work where you need it to work. This thing is not like that. As long as you've got a heavy thing here and something for it to pivot on here and something that spans the gap and a little finger that presses down, it's good to go, dude. And if you don't like this angle, you just bend it, right? It's one of the simplest first projects you'll ever build. I used an old tractor spanner, an offcut of round bar that was already just sitting around, bit of square bar, ditto, and a little bit of this rod here. And all I had to do to that was grind on a little point, put a little flat on the end, and then put a 90-degree bend in it, like piece of cake. And then with some of these welds, I just attack them with a carbide burr to make them look aesthetically a bit more pleasing. But the reason I suggest you make this is because you'll use it frequently for years and years and years. It'll last forever. And then you can look back and you can say, that's the first thing I ever made with a welder, and it's still working, so yay. So that's good for the soul as well. If you want another good first project and you've got a drill press, make a fixture plate like this. These are so powerful. They can really elevate your game, because not only will they allow you to stick a couple of things together and make sure they're at 90 degrees, like you can get one of these squares or a piece of angle and just clamp it to the plate, and then not only are these two parts at 90 degrees this way, but they're also true, like they're flat, okay? And you've really got to worry about this stuff whenever you're building anything square. And square is something you build a lot of when you weld, like you're always building frames kind of thing, shelving frames, or so many 90-degree angles all the time. And a flat plate like this, it's just right for setting up for basic square frames of this nature. Just clamp this to the plate. There's your clamping system. You just go, and your part is tacked. You can flip it and clamp it again and tack the other two sides, and then you don't need it anymore because it's clamped in place with 3 strippers, right? Very powerful. But there's a greater superpower to having something like this, and I'll give you just a brief example. Let's say I'm building something that needs cross supports, like a shelving system. I don't know, a ladder. You should never build a ladder if you're a home welder, because that's the sort of thing I'd leave to a professional. But hypothetically, you're building a ladder. You can set up a couple of stops like this, okay? Like this would be better. You can set up a couple of stops like that. And these stops, incidentally, come from a clamping kit, which is that. They got a whole bunch of straps like that you use for clamping on a machine table, typically like a milling machine, but they're very useful in the fabrication universe as well. And basically what that means is you drill all these holes, and half of these holes are drilled for M12 by 1.75, like metric course, 12 millimetre, and the other half are drilled for 16 millimetre. They're just plain 16 millimetre holes. So the small ones are tapped and they fit 12 millimetre screws. The big ones are plain and they fit clamps of this nature. So if I want to clamp this to the table, it's that simple, okay? So that's one of its superpowers. You also get, I'm gonna say, this kind of clap, and you can put that in place. It's like a vice grip kind of deal. It goes in the hole if the hole doesn't have a BB in the top of it. And you vice grip it to whatever you want to clamp. So you just adjust a little screw and you vice grip it into place. So that's kind of cool as well. But the real superpower here is how you can productionize just about anything. So if I want to put a bunch of rungs in here, I get these little screw-in stops that you can buy from welding shops. You know, they're pretty cool, but you don't have to use them. You could just go to a nut and bolt shop like boltandnut.com.au. They're in a good Australian operation. They'll sell you something like a shoulder bolt like this, which is M12 by 1.75 with a 16mm shank. They're very common in automotive for hanging suspension components off. You screw it up and then there's a precision ground shaft to put a bush on, basically, okay? So you can use shoulder bolts in lieu of this kind of thing, but you get this kind of thing in place and then you get some form of square. It can be a square like this or just a speed square, and you adjust two of these straps so that this and this are all of a sudden at 90 degrees. And you think, yeah, that's great, okay, bonus. But you can also do this. You can have another set of straps here, and you can have your next rung, let's call it, there. And then if you've got another 8 rungs to put in place, tack, 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 tack down there or something. You've got 3 tacks in place, you pick up the whole part and you can index it, right? You can index it to there, you can set it up and go next rung, tack, tack, tack. It's exactly the same distance from the first rung. You haven't had to measure anything. Once you've set this up, it's rinse and repeat, baby, and no measurement errors. Errors in welding are terrible because you spend so long with the grinder cutting it out, it always looks terrible. And you're not going to make any measurement errors with this because there's nothing to measure. You set this up, it's 1,000 jigs waiting to be built. And it's perfect, right? Because the next one is just, I pick the whole piece up, index it back this way again, and if this was longer, we just keep going. And the only thing I have to worry about is supporting it when it gets long out this way. But there's my jig that makes sure that I build this one-off thing with remarkable consistency, better than I could do it if I'm welding on the garage floor. And all I had to do was find a piece of scrap plate that's, I'm gonna say 200 by, it looks like about 500, but I forget, 480, okay? So this is a simple thing to build with a drill press. If you put it up on these wooden feet like this, then you can clamp around it as well. You can get any sort of simple clamp like this, self-adjusting thing, and you can clamp around it. You can go almost halfway. You know, you can clamp something to something else on the plate like that without worrying about screwing anything in or anything of that nature. Thank you so much for sticking with me. I appreciate the commitment that you've made in time to get across the line, and I hope this has been valuable to you. And I really hope you are going from 0 or crap to above average, because it's not that hard. It's really just a matter of sticking to the basics, those 4 things, the 2 angles, the stick out or the arc length, and the travel speed. Get the machine in the ballpark. You'll be off to the races before you know it, dude. But thank you for sticking with me. That means a lot to me because I'm not saying all this for me, I'm saying it for you, right? The final point is there are some things that you should never weld if you're a DIY welder, and I'll show you why. I made a couple of classic mistakes making these clamps, and the biggest one is here. These clamps are really simple. They just screw into the holes, right? They've got a bolt welded to the end of this cut-off F-clamp that I bought on sale, so really cheap. And then it's got a matching nut down here that I can tweak with a wrench, and it will hold the clamp in place. So I can clamp a part like this, weld it, undo it, move the clamp out of the way, put a new part in place, and it doesn't flop around, right? If I use a clamp like this, when I've got this here, it moves everywhere and it's harder to set up, and you're wearing the gloves, and you know, this is much better if you've got something you want to clamp in here and you want to put multiple parts through it. You just lock it in place with a wrench, okay? Then you're on top of what you need to be on top of. You clamp it in place, you weld, it's fantastic, okay? And the reason I don't mind welding this and the reason I don't mind showing you this problem is it's not something that's critical. Lives are not in the balance, but here's the mistake, right? I lost my orientation visually and I didn't have a plan about how to weld it. Welding round things is probably one of the hardest things you ever do because there's a lot of gross movement for not a lot of movement at the torch end, right? And with a gas shielded process, it means that instead of having the work angle where you want it at sort of half of the angle of the weld, it's really easy to get out of orientation and be welding in like this. And that means you're losing the gas shield really easily. And that gives rise to problems like this that didn't look too bad on the surface, but after grinding, you can see this cratered piece of embarrassing shit just here, which is a classic example of porosity. And porosity arises as a consequence of inadequate shielding generally, although it can also arise from contaminants in the material that you're welding, such as the welding scale, that black scale on hot rolled steel. But you can see that porosity is terrible. And on a clamp, it really doesn't matter, but it's not strong to start with, and it can potentially set up things like stress rises inside the joints. It degrades the strength of the joint in multiple ways. Now, if this fails and the clamp splits in half, I'm just going to grind it shiny again and weld it back up. Like, who cares, dude? But if you're welding at home, and I'm not a certified welder, I'm a dude who understands welding and worked in welding engineering and even designed some fairly ambitious things that were built, like a 100-ton dynamometer calibration rig that exerted 100 tons worth of load on a railway dynamometer. And it had full penetration butt weld on a universal coupler, right? That carried 100 tons of load with people working around it. So that matters. And I designed it and it didn't break, but I sure as shit didn't weld it. The dudes who welded it were qualified, certified welders. And that's why it didn't break, okay? I wouldn't trust me to weld something like that. Even if the chips were way down, dude, I wouldn't do it. And this is a roundabout way of saying that don't make your own ladders. Don't make your own A-frame gantry to lift engines out of a car, because if something fails and it folds up or a weld fails, someone could have their arm under the bloody thing and an engine could fall on it. The consequences of this kind of thing are terrible. There's so much stuff you can build working at home. You can build it with impunity, with no liability attached. And I'm not talking about legal liability here. I'm talking about moral and ethical liability. How would you feel if you whipped something up and it worked okay for, I don't know, 5 or 10 years, and you worked together with your son on it, let's say, and it's an engine crane or it's a gantry with a block and tackle on it to lift the engine out of a car, and he's working on his first car and it fails and it falls on his hand, and that's just endless months of microsurgery and rehabilitation. And how would you feel about that if that happened? So this is a roundabout way of saying, do the stuff that doesn't matter. Make barbecues and make brackets and make welders' third hands and make shelving systems for the garage if you want, and make a few Franken wrenches and do all of that kind of stuff, and figure out a great way to mount the bracket for your freaking filter for your plasma cutter. Or there's no limit to the kinds of things you can make that don't incur the burden of ethical and moral liability if something fails, right? All this ambitious shit like cranes and ladders and things of that nature, leave it to the pros.